Good morning, and thank you for joining today's webinar from SPEC Innovations, LaTeX plus Innoslate, Adding Math to System Models. My name is Taylor Duffy, and I will be the moderator for today's webinar. First, I would like to go over some housekeeping. During the presentation, feel free to send us questions, and we will get them answered in the Q&A part of the webinar. You can also interact with us on LinkedIn through the Innoslate users group or through Twitter using the handle @SpecInnovations. The webinar is being recorded and will be made available to you after the live presentation, so keep an eye out for it in your inbox. Now, I would like to introduce you to our presenter, John Schatz. John Schatz currently serves as the Vice President of SPEC Innovations. He has more than 30 years of postgraduate experience as a program manager, director of systems engineering, and various systems engineering and technical roles. He directly supports business development and technical performance with the U.S. Navy and other customers. Mr. Schatz designs tailored digital engineering environments to support DoD research and development and test and evaluation initiatives. He received his bachelor's in mechanical and aerospace engineering from Cornell University in 1991 and master's in electrical engineering from Virginia Polytechnic Institute in 1996. Feel free to send him any questions through the LinkedIn users group or email to marketing@specinnovations.com. Now I'll hand over the controls to John and we'll get started.
Thank you. So this is our agenda for today. We're going to talk about LaTeX in Innoslate and how that applies to computable attributes. We'll then look at parametric diagrams and see how we can use computable attributes to make parametric diagrams executable. But first, LaTeX is a markup language that supports complex mathematical notation. It's frequently used in published technical documents. Innoslate makes use of it to define mathematical expressions within the equation and computable attributes. So LaTeX includes a lot of things that Innoslate does not render. For example, matrices or arrays are not renderable within Innoslate. So looking at these circles here, there's the overall amount of LaTeX mathematical expressions. There's the ones that we can render, and then there's also a smaller subset of those that are ones that we can execute. So, for example, we can render integrals, but we cannot compute integrals. So, the types of things that we can typically compute are things like square roots, powered roots, powers, algebraic expressions, trigonometric functions, those type of things. Okay, so what is a computable attribute? A computable attribute is an attribute that is used for mathematical computations within Innoslate. The equations are specified in a LaTeX format, and they reference other entities' attributes. So in order to be able to make use of them, we need to do some schema modifications. Both computable attributes and the equation attribute are not in any of the baseline classes for Innoslate. So what I recommend that you do is create a subclass of one of those baseline classes to extend it. I don't recommend making the extensions within the baseline classes. It's always good to keep that as a clean baseline that conforms to the schema that other people might be using or other projects might be using within your organization. So I recommend creating a subclass. So for example, creating a computable equation subclass of the equation class. You can see over here on the right, we have the schema editor. In here, we've created one called computable equation. Its parent class is equation, so it's going to inherit all of the attributes and all the relationships and all that equation has. And then we're going to add that type computable. So here we click on the add attribute button. We provide an attribute name, and then we select the type to be computable. Now I'm going to skip ahead here to the part of the demo. I'm going to show you how to do that real quickly. So you're going to go to schema editor. In this case, we've already built the computable equation subclass. You can see here it's got a computable value, type computable, and it extends parent. I'm going to go ahead and do this again for another one. I'm going to call this one renderable equation. I'm going to make it a subclass of equation as well. And I'm going to add an attribute. We'll call this, let's not be original, we'll call it renderable equation. I'm going to make this one type equation. Instead, we pick type computable for the other one. And then that's all we need to do. We just hit save, and it will show up there in our schema. There's a renderable equation class now, subclass. So that's exactly what we did with our computable equation one. So going back to the slideshow, now that we've created this computable equation subclass, what do we do with it? Well, we can go ahead and we can define a computable equation. In this case, I'm going to go through an example. This is a room volume calculator. So when we talk about a room, it's got length, it's got width, and it's got height. So what I'm going to do is I'm going to create characteristic entities for the room's length, width, and height. And in the value field of each of those, I'm going to put the values of those variables, and then those will be made use of in this equation. So we start out by either creating a new computable entity with a computable attribute or opening an existing one. We then go and we select that blue compute button, and it'll pop open a window where we can define our variables that are going to be used. So what we're going to want to do is we're going to want to select the entity that contains the variable. So in this case, I'm picking the one called room length. Then after we've got that, we're going to pick the attribute that we want from it. So in this case, I'm going to pick value. That's where I stored my number. And then I'm going to give it a name. So I'll give it the name L for length. It's good to keep these short because you're going to need to use them in the equation. And then we're going to click the add variable button. So you can see here, I've done it for all three of these, added length, width, and height. You can see they've got different values. In each case, I'm pointing to the value attribute of those characteristic entities, and here are the names of the entities. So once I have those variables laid out, those are the things that I can use in the equation. I'm going to click on the next button. And what it'll do is it'll pop open another window that'll allow me to enter the equation. So I'm going to go ahead and I'm going to type in the equation. You can see here I've typed in L star W star H for length times width times height. What you're seeing there is a very simple LaTeX equation. And then I'm going to type in the result in units. In this case, it's cubic meters. I'm going to hit the compute button. So after I do that, it's going to display the result. You can see here it says it's 30 cubic meters. I can adjust the number of decimal points if I want to, either up or down. In this case, I can't go down, so it's grayed out, but I can go up. I could make it more. And then I'm going to hit finish. And when I select finish, what it will do is it will take the value and it will take the units and it will put them back within the entity view so you can see them. And then you're going to need to save that entity to persist those values. Okay. Going on to parametric diagrams. So we'll talk briefly about the parametric diagrams, then I'll come and I'll tie back in the computable attribute and show how we use it. So parametric diagrams, they're SySML diagrams used for modeling mathematical equations. The one you're looking at down here at the bottom is a model of a police radar speed computation. So it's got a radar gun, it's got a vehicle, it's got some constants and a number of equations that have to be calculated to assess the Doppler shift that's seen in the speed computation. So within this diagram, we have some elements. There's a block. A block's a system or part of a system. And in this case, the one I'm circling here is the vehicle itself. And it's modeled with an asset entity within Innoslate. You don't need to know that to use the diagram, but that's what it's going to put in the system. Then we have values. So values are something that describes a quantitative property of that system. So in this case here, I've got the actual speed of the vehicle, and those are characteristic entities within Innoslate. We also have within these parametric diagrams, constraints. Those are mathematical expressions. So we got a number of them here. We're pointing at this one over here. So those are equations within Innoslate. one thing to note is, there are equations, but when an equation is a parent class, you can also use any of the child classes. So we're going to make use of that when we use our computable equation subclass. And then we have parameters. Parameters are variables within a mathematical expression. So they're the little squares you see here, and those are characteristics also within Innoslate. So how do we make that parametric diagram executable? Well, we need to somehow use those computable attributes to do that. And the way to do that is first we create that computable equation subclass like we did, where we add a computable value to an attribute to the equation class. Then we're going to want to take each of those equations, in this case there's 4, 1, 2, 3, 4, and transform those to the computable equation subclass. And during the demo, I'll show you how to do that. And what that'll do is it will add that computable field onto those. Then we're going to store our initial variables in the characteristic value attributes. So things like actual speed, speed of light, source frequency of the radar gun. Those are all going to be characteristics where we're going to want to store those values. I'll also go over how that's done in the demo. Then we're going to make use of the computable value in each of the equations and store our computed values. The last bullet here is especially important, so take note of that. You need to execute and save the constraint computations sequentially. If you don't do the save part, you're going to end up with the previous value that was stored there. So if you've changed say the actual speed of the vehicle from the last time you ran the equation, and you fail to save after each of these steps, you'll be using whatever was there from before in your numbers. So it's very important that you persist the changes that you've made to that entity and that computation. Otherwise, you're going to get bad downstream values. So you can see here in this computation for speed, it's the final computation in the radar gun model. We're making use of two initial variables. We're making use of the source frequency of the gun and the speed of light, but we're also making use of a computed value for the radar Doppler shift. So we have to make sure that one's been saved before we make use of it. Okay, so now I'm going to go ahead to the demo. We've already done the part on creating an equation subclass. I'm going to go ahead and we'll talk about transforming equation entities using computable attributes and executing parametric diagrams. So I'm going to go ahead and I'm going to open up this model that I've created. It's a relatively simple model, and it's going to create or it's going to implement a calculation to determine the number of gallons of water are within a pool. So we have a pool here. Pool's got two characteristics associated with it: the pool radius and the water depth. And we have a constant out here. This constant is the number of gallons per cubic feet of water, how many gallons equate to a cubic foot. And then we got 3 equations here. Now, I could have taken all these equations. I could have done them all in one step, but I wanted to keep them in 3 to illustrate the saving between the individual computations, so that you can make sure just to drive home that you need to persist things before you use them in your next computation. So let's look at these. So we have the pool area. It's an equation, and you can see the attributes that are associated with it. It's got a value attribute. It's got a description field. It does not have a computation field. So that and all the others are going to be the same in that regard. So the way we can change that is we can either open them individually in entity view, or as I would prefer to do, go to database view. In this case, I'm going to filter on my equations. I've only got 4. One is the top level of that diagram we saw. The other 3 are equation 1, equation 2, and equation 3. I've numbered them in the order of my order of computation because that will help me down the road. So that's why they have the numbers they do. I'm going to go ahead and I'm going to do a transformation on these, picking the computable equation class to transform them to. And I'm going to go ahead and transform. It asks me if I want to save all the current changes. So I'm going to say yes. And now I've got these 3 here. Let's pick one. We'll pick the pool one. You can see it's now got this compute field over here in my sidebar. And you can see that it's changed from being an equation to a computable equation class. So let's go back to the diagram. Okay, so within the diagram, we're going to start at the top. We're going to work our way through the computation sequentially. So for the first one, that's the pool area. I'm going to go ahead and I'm going to click compute. And it's going to ask me what variables I want to get. So in this case, I only have one variable, and that variable is the pool radius. So I'm going to go find that. And I could number these if I want to, or sort on them to help make it easier if I had a lot. I'm going to want the value. I'm going to give it a name. In this case, it's going to be R for radius. That's the only variable I need. In this case, we had the value 6 in there. I'm going to hit next. It's going to ask me for an equation. Now within LaTeX, pi is a constant, so I can just type in pi, pi. And I'm going to multiply that by the radius squared. So I'm doing R and then the up caret and then 2. And it'll create that equation in there. And in this case, the resultant units are feet squared. And I'm going to hit compute. So it comes back with the area. And I'm going to go ahead and hit finish. And now I can see that area, 113 square feet, is showing up over here. Now, for the sake of showing how this works, I'm going to go in. I'm not going to save it. I'm just going to go to my next one here, my pool water volume, and I'm going to do that computation. So what do I need for that? I need the pool area, and I need the water depth. That's going to give me my volume in feet. So I'm going to go ahead and calculate this. I'll pick the water depth, and I'm going to get the value attribute. Call it WD. I'll add it in there. And then I want the pool area. That's in my calculation of that. We're going to use the computable value, not the value. And I'm going to put in PA for that one. I'm going to add it. And you can see it's put in the value as 0 down here. That's because I did not save that pool area entity after I did the calculation. So it's got the last value that was in there, which was 0. So I'm going to go ahead and I'll continue to work this out here. I'm going to put in my equation. My equation for the pool volume is PA, pool area times water depth. Resultant unit is going to be feet cubed. I'll compute. It'll come back with 0. I'm going to go ahead and finish it. Now I'm going to go out here and I'm going to save. Back into the diagram. You'll see when I open up this one to compute it the next time now I've saved what was in there. So PA is updated to 113, but I have to rerun the calculation again. So I'm going to go through. I clicked finish on the first screen saying I had the right variables. I'm going to recompute it, and now it comes up with 226 cubic feet. So it was 113 square feet surface area and then 2 feet depth. I'm going to finish that. Click out here in the white space, save it, come back in. I will show you an easier way to do this when I change the variables in a minute. So we'll do the pool water in gallons computation next. So here's the computation I'm going to implement here. I'm going to take the pool volume in cubic feet, multiply by the conversion factor. So I need to get that gallons per cubic feet. I want the value field. I'm going to give it a name, gallons per cubic feet. Add that variable, and I'm going to go get the pool water volume. Once again, I'm picking the computed value here, not the value. The value field's empty. And I'm going to call that pool volume and add that variable. I'll go to next, and my equation in this case is going to be pool volume times gallons per cubic feet. Resultant unit is going to be gallons. I'm going to compute. So it's going to take 1,692 gallons to fill the pool. I'll finish. I'll go ahead and save it. And now I'll come back into the diagram. Okay, so that's roughly the process we're going through. Going to have to go through to run that computational thread. Like I said, you could have done all this computation in one single equation entity. I just wanted to show how it would need to be done if you're doing something that is a little more complicated and requires a sequence. So now what I'm going to do is I'm going to go ahead and change the pool radius to 7 feet. And I'm going to change the water depth to 3 feet. And I will then walk through how we can do that computation a little quicker. Okay, so we could go through, once again, selecting these, doing the computation, saving it, coming back into the picture. The quicker way is to go into database view where we have our equations already here. I'm going to put them in order, numeric order, and I've got them numbered 1, 2, and 3 for the number that I need to execute them. So I'm going to go into the pool area one. It's got new values for those variables now. So it was 113. Let's go see what happens. See, it's changed the value of R to 7 now. It was 6 before. I'm just going to hit the compute button again here. It updated it from 113 to 153. I'm going to hit finish, come out here, deselect it, hit save. I'm already since I'm in database view, I'm already at the right screen. I don't need to go back and forth in and out of the picture. So I can just run this sequence of items here. You can see here the water depth's now 3. The pool area went up to 153. So I'm just going to recompute and get new numbers. Once again, deselect it and save it. Now I've got that persistent value for the next equation. Here we were at 1692. We're going to go through, look at it with the new values. Compute. Now it's 3454. Finish, deselect, and save. And once again, I can see this same information here in the parametric diagram. So going back to the slideshow, I think we've hit all these things in the demo. We showed how we can create an equation subclass or a whether it be with the computable attribute or the equation attribute. We showed how to transform those equation entities in database view, but you can also do that in entity view one at a time. We've showed how we create and use those computable attributes, and we've demonstrated how to tie that to parametric diagrams and execute a parametric diagram. So that is all I have for the demo, and I think at this point I turn it over to Taylor again.
Thanks, John. John does much of our training at SPEC. If you're interested in our training opportunities, you can reach out to him or go to our website. Next slide, please. If you're interested in having our team help you add math to your project or system, contact our sales team to get you started. You can reach them by email at sales@innoslate.com or through our website, specinnovations.com/contact-us. Next slide. You've received several questions already. If you haven't done so, please send your questions through the panel on the right that pops up after clicking Q&A on the top bar. You will answer as many questions as you can before our time is up. First question is, what is the benefit of having a parametric diagram?
Yeah, so parametric diagrams are part of the SySML model. And I think the biggest benefit to having them is that they can allow you to visualize what's going on in an equation and where the different variables are coming from and what all those variables are. So they're mostly a visualization tool. They can be useful in briefing slides. That's really their primary benefit, is to help document where those things are. Now, another benefit by putting them in Innoslate and using them in Innoslate is that those elements that are there are relatable. So we can now tie them to things. So for example, in our model of say the pool here, if we had some type of an issue and we wanted to tie the issue to water depth, maybe we were trying to find out what is the optimal water depth, or what is a safe water depth for the conditions that we're creating the pool for. Maybe it's a kiddie pool, maybe it's an Olympic pool. We don't want an Olympic diving pool where people are going to dive into 2 feet of water. We don't want a kiddie pool that's going to be 10 feet deep. So there may be issues that we would be able to relate to those characteristics and have that all captured in Innoslate. So that's one reason we want to, that would be good to be able to put that information into the tool. But as I said, having this visual is useful in slides and briefing and informing your audience.
Does Innoslate convert between units when implementing the calculations?
Yeah, so in these equations, Innoslate does not convert between units. So it's up to you to make sure that you're using consistent units. So if you use let's say feet for the diameter of your pool, and you use meters for the depth, your volume is going to be in feet squared meters. It's not going to be in feet cubed, and you need to make sure that all your conversion factors and your units are consistent with each other. It will not do that automatically. It does not. Someone could put in feet spelled FEET or FT. Someone else could put in gallons spelled GAL or capital GAL or spelled out gallons. It does not make those choices for you, and we do not have a pick list associated with the computable equation attribute. So you will need to make sure that you do that on your own, and just that you're putting things in that are compatible with each other. So there's no conversions going on in the background.
Thanks, John. That looks like all the questions we have for today. Go to the next slide, please. We would like to thank you again for joining us today. As a reminder, we'll be following up with you very soon to send you a link to the recording and the presentation slide deck. We hope you can join us for next month's webinar, Verification and Validation using Innoslate's Test Center. John Schatz will once again be our presenter and share the advanced capabilities of Innoslate's Test Center in supporting rigorous verification and validation processes. Your link to sign up will be in the email that is coming soon to your mailbox with the slides and recording. Next slide. We also encourage you to visit our website and our blog, as well as connect with us on social media. That concludes today's presentation. Have a wonderful day, and we hope to see you at our next webinar.